The amazing Samantha Garza is a senior physics major who also did research at the University of Wisconsin-Madison, but also was a NAC alum, a NAC student the previous year, so 2018. This past summer, Samantha was working with Dr. Matt Ashby at the Harvard and Smithsonian Center for Astrophysics, looking at stars and how they form in giant molecular clouds from the Whirlpool galaxy. Samantha is also a president of the University of Dallas Society of Physics Students chapter and secretary of the Women in STEM Club, also very highly involved in astronomy public outreach, and is looking to apply for grad schools. So you can take it away now.
Okay, great. So thank you for that introduction. And yes, I'm going to tell you guys about my project this summer studying GMCs and CO to dust conversion factors in the Whirlpool galaxy, which is this beautiful galaxy that you see here on your left. So let's start off with a little bit of background. My project is focused on star formation and how it proceeds, since it can tell us many things about the inner workings of the galaxy, like how stellar populations and their orbital mechanics can change over time. So to gain a better understanding of how star formation progresses, we decided to focus our study around giant molecular clouds, or GMCs, because they're where star formation primarily takes place. And GMCs are typically several tens of parsecs in diameter, and the physical conditions within them are the principal drivers that govern star formation rates. So you can see the scale of GMCs in M51 in the simulation that's put out by PAWS, which maps the central part of the galaxy in CO 1 to 0 line emission. So the GMCs are shown in red, and they're surrounded by other molecular gas, which is depicted in that bluish gray color that you see. And so they're usually located in the spiral arms, where measurements of fundamental properties like cloud mass and star formation rate can be made through accurate measurements of the thermal far infrared or thermal far IR. So a recent study capitalizing on this idea of using the far infrared to measure dust emission in GMCs to infer dust masses within M31 or the Andromeda galaxy is Forbrich et al. 2020, which from now on I'll just call Forbrich. And so using SMA CO2-to-1 continuum and line emission of identical high resolution, they presented the first resolved continuum detections of dust emissions in individual GMCs beyond the Magellanic Clouds. And so using a dust model and an assumed temperature of 20 Kelvin, they were able to calculate GMC dust masses, and then to determine total molecular gas mass, they also found a CO to dust conversion factor, or alpha, using measured dust masses and CO luminosities. So this plot here on the left shows their conversion factors for resolved sources, which are in the blue dots, and unresolved sources in orange dots. In addition, a central idea from their study is that they showed there is significant CO2-to-1 emission in the thermal broadband emission, and also because they had a few high outliers in their CO conversion factors, as shown here. They showed the potential importance of CO contamination in existing thermal far IR measurements, which likewise cause a potential bias in our understanding of the inferred star formation rates for GMCs. So to further investigate this, we believe that the Whirlpool galaxy, or M51, represents the next ideal target for characterizing individual GMCs to get accurate masses and CO to dust conversion factors. Since it's nearby, the GMCs in M51 provide a unique opportunity to quantify the amounts of dust and gas in the galaxy, since these large clouds are bright, easy to identify, and relatively free from obscuring effects of unrelated foreground dust, kind of like the effects that Leonardo was talking about. So for example, in this infrared array camera, or IRAC 8-micron image taken with the Spitzer Space Telescope, you can clearly see the GMCs as the black dots located in the spiral arms. M51 is also almost face-on, which is different than M31, and allows us to clearly pinpoint the GMCs along the line of sight, again without those blending or obscuration effects. So by using a range of ground and space-based observations, we aim to derive dust masses and CO to dust conversion factors for individual GMCs in M51. Okay, so my first goal this summer was to use the Colombo et al. 2014 catalog to identify GMC candidates and then establish ideal GMC targets that were able to be suitable for photometry across our chosen infrared observations. So our target identification process was based on a list of GMCs presented in the Colombo et al. 2014, or for now on just Colombo, that use PAWS, or that data that I showed you in the simulation from earlier. So to begin the narrowing down process, we utilized our highest resolution image, the IRAC 8-micron mosaic, which can be seen here on the left, and our lowest resolution image, a Spire 250-micron mosaic, which is shown here on the right. The IRAC image was used to identify the bright GMC candidates, and the Spire image was used to finalize the GMC count to 33 by enforcing an isolation criterion to minimize source blending. To maintain the integrity of our photometry across our wide range of wavelengths, the spire mosaic was also used to set the aperture diameter, which is these little green circles that you see on both images. And they were set to about 1.5 times the full width half max of the spire beam, which came out to be approximately 27 arc seconds. And also by using our lowest resolution image to set the aperture diameter, we ensured that all of the regions in our observations were bright and isolated enough so that we could capture all the light emitting from the galaxy and therefore have reliable photometry. So my second goal this summer was to perform photometry on our now 33 GMCs in the thermal far infrared wavelength range from 24 to 250 microns, SMA CO2 to 1 emission lines, and H alpha imaging. And so by using the Python AstroPy package photutils, I performed photometry on the GMCs using the aperture size that I mentioned earlier across all the observations that we used. And from these photometric measurements, I was able to measure flux densities, integrated line intensities, and star formation rate estimates, which I then used to derive dust masses and CO to dust conversion factors. To derive the dust masses and the GMCs, we use the reliable method of creating broadband spectral energy distributions, or SEDs. And for our SEDs, we plotted flux density in Janskys on the y-axis versus wavelength in microns on the x-axis, as you can see in this plot on the right. And so by using the thermal broadband emission photometry, we quantified the dust mass in our individual GMCs using an SED fitting routine that I created that used set temperatures to model the cold and warm dust. My fitting routine utilized a 2-component blackbody function that fit to 4 photometric far infrared observations. And so for the first component, we modeled the cold dust. We followed Forbrich and set the temperature to 20 Kelvin. And so you can see the cold dust right here is this blue line. And then for the second component, which modeled the warm dust, we followed Magaphis, which cites the warm dust component emission in nearby galaxies between 30 and 60 Kelvin. And we found our best temperature to be 50 Kelvin, and that model is represented in the red line right here. We then added the 2 components together to get a total dust model, which is shown in black. And just for reference, this is a representative SED for the 33 SEDs that I made. And from all of these, we got a mean total dust mass of 5.78 times 10 to the 5th solar masses, which is similar to masses that we found in literature, so it's exciting. But interestingly, in all of our SEDs, we found that our 160 micron observation, which is shown right here for GMC 8, always lies above the total dust model. And so we find this intriguing, and we speculate that this may be due to possible CO contamination in the thermal far infrared, which is something that Forbrich talks about in their paper. Using the same photometric methods that I used for the thermal far infrared observations, I got CO 2-to-1 integrated line intensities for the GMCs, which I used to calculate flux, CO luminosities, and gas masses following the equations presented in Colombo. And as a check to see if our derivation methods were valid, we plotted the thermal far infrared dust masses against our calculated CO 2-to-1 luminosities to see if we could show the clear trend between the 2 parameters that they cite in literature. And as you can see here in the plot on the left, we're able to find a strong positive correlation between the 2 parameters with the correlation coefficient of 0.95, which justifies our derivations. Now, as I mentioned before, having accurate measurements of the CO to dust conversion factors provides us the opportunity to further understand the processes that regulate the majority of star formation within our galaxy. And so following Forbrich, we calculated our alpha factors using this equation below, where M dust is for the thermal far infrared dust masses, ICO is the CO flux, and then A is the area of our GMC apertures. And from this, we were able to calculate our alphas, which are shown here in the plot on the left. And we find that including our outlier, all of our values are a factor of 3 larger than those presented in Forbrich. So we don't fully understand why our factors are higher than those found in Forbrich, but we do suggest that this difference could come from several different factors. So it's possible that they are higher because we used our larger apertures, which are again set by that lower resolution spire mosaic, or because there's that CO contamination hiding in the thermal far infrared mosaics, which we performed our photometry on, again, evidenced by that 160 micron observation that lied above the total dust model, and possibly due to incomplete thermal far infrared modeling, since we only fit to 4 photometric points, so it wasn't a complete model. Finally, we were able to estimate star formation rates for individual GMCs that we performed our photometry on using a star formation rate image observed this summer using the Spitzer Observatory in Crete. And so this image shown on the left was generated by converting a continuum subtracted H alpha image into that star formation rate map using a conversion that was described in the 2008 Kennicott paper. And since H alpha has become to be known as the gold standard for estimating star formation rates, we believe that we were able to get accurate values for our 3 GMCs. And those rates are depicted in the histogram on the right, which has a bin distribution of 0.12. And so from these, we were able to find a mean star formation rate for our GMCs to be 0.05 solar masses per year. And we will find this to be reasonable since the star formation rate for M51 as a whole is approximately 3 solar masses per year. And since we're only looking at those individual clouds within the galaxy, we find this rate to be valid. And from these star formation rates, we were also able to calculate star forming lifetimes for our GMCs. So following Forbrich, we multiplied our measured thermal far infrared dust masses by a dust to gas ratio to get the total molecular gas mass for our GMCs. So by multiplying our masses by a ratio of 136 and then dividing this new total molecular gas mass by our star formation rates, we're able to get a mean star forming lifetime of approximately 2 gigayears. And so to investigate this lifetime further, we explored the proportionality of the star forming lifetimes against our dust masses, and that relationship is shown here on the left. And as you can see, there's not really a significant correlation. So we speculate that this may be due to a lack of precise estimates for the physical conditions within our selected GMCs and suggest that further research is required. So speaking of further research, we actually have submitted an SMA proposal to measure the CO3 to 2 continuum emission within M51, so we can further constrain those calculated dust masses and those conversion factors. We did this because since we measured those higher alphas than Forbrich, and they show evidence of CO contamination within their thermal broadband emission, we speculate that we also may have values that are overestimated due to that hidden CO3 to 2 emission that's contaminating our, for sure, 160 micron and possibly our 250 micron observation. We also plan on investigating the CO1 to 0 emission line data from PAWS to gain a better understanding of the physical processes contributing to star formation in the GMCs. And also by studying this different line, we'd have another set of CO to dust conversion factors to compare to from the alphas that we calculated using the 2-to-1 emission line. So lastly, I'd like to give you a quick summary before I open the floor for questions. So one, we performed photometry on 33 GMCs in the thermal far infrared, CO2 to 1 emission lines and H alpha observations and observed dust and gas masses, as well as found star formation rate limits for all of our clouds. Two, we calculated conversion factors from the CO2 to 1 integrated intensities to be only a factor of 3 larger than those presented in Forbrich. And three, using H alpha derived star formation rates and calculated total molecular gas masses, we found a mean star forming lifetime of approximately 2 gigayears. So lastly, I'd like to thank my advisor, Matt, and all the CFA staff who made our remote RU opportunity possible, and of course, the NAC program for their continued support. Thank you, and I'll now take any questions.
Thanks, Samantha, for a nice talk. I wanted to ask about the isolation criterion that you had to impose in order to ensure that your photometry was well matched. Does that lead you to end up with a different range of cloud sizes from what was in the Forbrich et al. Sample, for example?
Yes, because you can even see from these two images, like in the Spire mosaic, they're super pinpointed, and you can even make smaller measurements. So some of them, like if, for example, in 9, it's kind of blending between what could look like 3 GMCs, but in the Spire 250, this one just looks like one big clump. And so we were torn between how we were going to do this isolation criterion, and we ended up going with bigger sizes so that we could get initial values. And then actually this semester, next semester, we're hoping to close in those gaps and make smaller and smaller values so we can get better estimates.
And is the factor of 3 sort of offset that you mentioned, is that like taking exactly the same clouds that Forbrich et al. Were looking at, or is that just a statement about like the average values that you're getting?
Those are just their average values that they got. So we're not using the exact same cloud since they used a different galaxy. Oh, okay. But based on their size and the previous study using the Colombo catalog, which we created to get these GMCs, that's where we're getting our factor of 3 from. Okay,
cool. Thanks very much.
Throw blanket praise. You did this in a summer? Is that?
Yes.
Holy crap. I mean, that is this is a huge project. It's amazing how much you got done. I mean, really, really amazing. And very cool results. I had a question on slide number 10, which was your alpha plot. So you had one outlier, you said, which is
yes,
pretty clear. But what are the uncertainties here on your values?
Um, I was hoping no one would point that out. We're still working on the uncertainties. This was a plot I made right before the summer, and so I'm still going back and figuring out that element in the code. And we don't have anything to put it against since these are all new. So I'm still doing literature and trying to get the accurate measurements, but they're, I think about like half an order of magnitude, so not too great. So these are pretty precise, but they're okay.
So the outlier really is an outlier, and that factor of 3 systematic offset seems large too.
Yes. So if we take away the outlier, it's still a factor 3. We're not including it since it's completely an outlier. Cool. But the systematic uncertainty is pretty on par with what Forbrich found.
And then I just wanted to double check. You're using a constant dust temperature in your modeling?
Yes.
Okay. Any bad solutions? I mean, I saw there seemed to be some multiple components and things like that, but you know, this is a tricky game in the Milky Way, at least, because the dust temperature varies. That beta factor, you know, varies, especially in some very weird regions that gets kind of haywire, and then they're correlated and nobody knows why. So anyway, I was curious about that. That could throw a lot of systematics in there. And I had a suggestion if you hadn't seen it, but the Planck team pulled the CO 1 to 0, 2 to 1, and 3 to 2 intensities out of their broadband data. And so there's a really nice, line to continuum estimate there from the Planck survey that might inform your CO3 to 2 contamination to your particular broadband measurement as well in the infrared.
Okay, thank you. We'll definitely look into that.
Yeah, their signal to noise wasn't great on the CO3 to 2, but it's pretty good, you know, and you could lump it all together maybe. So, you know, that's like Planck 35, you know, one of those papers. Check it out.
Yeah. But yeah, to answer your question about the set temperature, we considered doing a vary temperature, which the mentor who also helped me, she had a vary temperature within her SED fitting code, but we decided to set the temperature to see what the results would be. And then I'm working on a code to vary the temperature right now.
Very cool. Again, I'm just blown away by how much you got done in one summer. It's amazing.
Oh, thank you.